Have you ever wondered what it would take to turn a simple picture, just a regular 2D image, and almost magically transform it into a real, physical 3D metal object? I mean, it sounds like something straight out of science fiction, right? Well, it's actually the new frontier in manufacturing. Today, we're going to break down some amazing new research that's building a direct bridge from the pixels on a screen to a custom part you can hold in your hand. All right, let's get into it.
So here's our roadmap. First, we'll talk about why making custom parts is so tough. Then, we'll check out a really clever solution called SPIF and how that actually created a new kind of problem. From there, we'll see how Python comes to the rescue, put it to the test against the old school way, and finally, look at what this all means for the future of making things. Okay, so first up, the big challenge. Why is it so hard to make one-of-a-kind metal parts? Well, it really all comes down to the high cost of being unique.
Think about it. If you're in aerospace or the auto industry, or even making custom medical implants, the traditional way to do things is to create these massive, super expensive molds and dies for every single new design. This just blows up the cost and the time it takes, which makes producing just one prototype, or maybe a handful of custom parts, pretty much a non-starter.
But what if you could just get rid of those expensive custom molds altogether? This is where a really, really smart process enters the picture. It's called Single Point Incremental Forming, or SPIF for short, and the idea behind it is just brilliant. Instead of stamping a whole sheet of metal at once, a single, simple tool controlled by a computer just moves across the metal sheet. It's almost like it's drawing on it, slowly pushing and shaping it, bit by bit, into a complex 3D form. It literally draws the object into existence. And when you put them side by side, the difference is just night and day. On one side, you've got traditional forming. It's expensive, it's rigid, it needs those custom dies. But on the other, you have SPIF. It's a dieless process. That makes it absolutely perfect for low-cost prototypes and small batches. And here's a cool bonus. This gradual shaping process actually makes the metal more formable so you can create even crazier shapes. So, SPIF is awesome. It totally solves the hardware problem. But as it turns out, solving one problem can sometimes reveal a brand new one, a new bottleneck in the system. So you're probably asking yourself, okay, if the SPIF thing is so great, what's the catch? Well, the problem isn't about shaping the metal anymore. The problem is telling the machine how to shape it.
See, the workflow to get there is still pretty slow and clunky. An engineer has to sit down and create a 3D model in CAD software. Then they have to export that to another piece of software, called CAM, where they manually plot out the path the tool needs to follow. Then they process that into code the machine can understand, and only then can the machine finally get to work. It's a lot of steps, a lot of manual labor, and a lot of places for things to go wrong.
And this is where the research gets really, really cool. The whole goal was to use Python to build a completely automated bridge, a direct path, from a simple 2D image straight to a finished metal part. No more manual steps.
So the researchers basically set up a showdown between three different methods. First, you have TCAM, the traditional way which uses fancy algorithms to make smooth curves. Then they cooked up two new methods using Python. The first is called PPM, or pixel modeling. This one is so clever, it just looks at an image and turns the brightness of each pixel into a height. So a brighter pixel means a higher point on the model. The second Python method is PED, or edge detection, which uses computer vision to find the outlines in an image and basically traces them to create the toolpath.
All right, so with our three contenders all lined up, the old champ and the two new Python challengers, it was time to put them to the test. They decided to make three different parts, a frame, a leaf, and a tree, to see which method really came out on top.
And here's where we get our first big surprise. When you look at how long it took to actually make the parts, you'd think the new automated Python methods would be faster, right? Nope. The data shows that the old-school traditional TCAM method was actually the fastest of the three.
And when it came to being precise, well, the difference was even clearer. The traditional TCAM method nailed a final dimensional accuracy of over 97%.
Looking at the full breakdown here, you can see TCAM just crushed it. It had the lowest error rate by a pretty wide margin. The Python methods, they worked, but they just couldn't match that level of precision. The pixel modeling method had almost twice the error, and the edge detection method was even further off.
So, the new methods were slower, and they were less accurate. Case closed, the old way wins, right? Well, not so fast, because the real win here isn't about who was fastest or most accurate on this particular day.
So why is this such a big deal?
Because the real breakthrough wasn't about performance, not yet anyway. As the researchers themselves put it, the novelty was in creating a fully automated Python framework. For the very first time, they proved that you could completely eliminate all those manual, time-consuming CAD and CAM steps. They built the bridge from image to object, and that is a huge deal.
So, let's wrap this all up. The big takeaway here isn't that the new methods lost, but that they succeeded as a proof of concept. Yes, for right now, today, if you need a super precise part, the traditional TCM workflow is still your best bet. But what this research proves, without a doubt, is that a direct, automated pipeline from a simple image to a physical part is no longer a fantasy. It's real. And that is a massive first step towards a future where manufacturing is truly on-demand, accessible, and customized for everyone.
This whole idea just opens up a universe of possibilities. It really leaves you with a fascinating question to chew on. If you could take any image you could possibly dream up and turn it into a real, physical object with just the click of a button, what would you create?